Thank you, Andreas. Yeah, I'd like to just take this thing. I'd like to introduce that research project we've been doing with the Czech Geological Survey and our partners from Finland. There are many aspects to the project, but I'll be focusing on, and Roberto as well, the methods and results from our stream sediment sampling that we've been doing on the Czech side of the Ore Mountains. So just to give you a brief idea of this aspect of the research project, the goal basically is to develop a geochemical method for deep exploration and accelerate the data acquisition and the exploration costs, bring them down, and with the goal towards generating sustainable and environmentally friendly exploration technologies using superficial media. So rather than spending a lot of money drilling holes, we'll try to use new inventive methods that are not as expensive to get results about deep-seated information from prospective areas, basically. And also, as you may be aware, there is a strategic mineral initiative from the European Union, and part of this project also is to raise awareness for the need for specific types of ore deposits and metals. And one way to do this is, that's quite an established method, is using stream sediment sampling to obtain information that has been basically copied through from below ground, and use these surface materials basically to find potential distal footprints of deep-seated mineral deposits. So this is our sampling area. You can see it borders Saxony and a little bit Bavaria, but lies completely in the Czech Republic. The area size is about 1,900 square kilometers, and we had 500 points for taking samples, which comes out to about one sample every 4 square kilometers. And we basically have the stretch you can see here of about 150 kilometers with a width that varies between 10 and 15 kilometers as well. And the red dashed line is basically our sampling outline. One of the other goals was, as was mentioned previously by Andreas Barth, is to, we have all these sampling points from a previous campaign called Vistamerts. And of course, the goal here is to use our data and combine them with the results from this campaign to create a combined database, and using the results and interpreted geochemical signatures across the entire area, because of course the geology doesn't stop at the border. So what kind of data did we use? We start off with a digital elevation model with a precision of 5 meters, and Ines and other people kindly provided help in taking out certain artificial things like dams and bridges and roads to calculate the things we needed later on, which is we computed stream orders. You can see here in colors, these are the stream orders, which one being the smallest types of streams, and you can see here in blue 5 and 6 are the major rivers. And so based on the digital elevation model, we're able to calculate, which is also quite an established method, our stream orders. Based on that, we computed the watersheds. You can see here in the outline quite gray, and by definition, the watershed is an area that collects all the water from a certain subset of streams or stream orders. So that gave us an idea of the amount and size and shape and location of the watersheds, and based on that we went in and determined where our sampling points would be. Certain areas were off limits because they're protected areas or they're just private land where we didn't have access. So we then figured out where to put our sampling points to cover individual watersheds that I've shown before. And yeah, one side note, by default or by definition, we want to catch and collect samples from stream orders 1 through 3, because the bigger the streams are, the bigger the watersheds, and the signal gets lost. If I take a sample here, that means all the material from all these subsets get collected, and I don't know if I have a high value, I don't know when I sample it here where it comes from. Whereas if I take a sample here and I get a high value, I know it's going to be from exactly this area. In terms of sampling procedure, I just want to highlight the ones shown in red here. That's quite an established method that is clearly defined. We collect ideally material from across the entire channel, and we then sieve it through this 2mm sieve and transfer all the material into bags. The really important thing is to rinse out the bucket carefully to get the finest fractions, because heavy minerals oftentimes occur as small, heavy grains. When you put it in the bucket, it sinks to the bottom, and then if you just throw out the fine stuff, you'll lose an important signal. So collecting the finest fractions is very important, and we record all our information on a tablet, so there's no scribbling in notebooks anymore. The location, we can take pictures, we can describe it, and so at any point in time, we can go back to exactly the spot where we took the sample. We can orient ourselves. We can actually find the spot on the river if we take the right samples to find, if need be, the exact precise location where we took the sample. These are just some impressions of what the environment was. Teams from Beak and students from Karlsruhe University in Prague were building two-man teams or two-woman teams to collect samples. You can see here the environment was quite diverse, and this is a sieve, and we basically throw out all the materials that the sieve catches. So anything that passes through, which is everything up to 2mm, will be collected in these bags. We also had a chance to meet some of the local wildlife. There's even a street sign that warns that there might be snakes around, which I hadn't seen before. But so it was quite nice, and actually it also gave us the opportunity to provide the students from Karlsruhe University with some field experience and get an insight into how scientific work is conducted. And so this is basically what we ended up with. We took 2 samples from each location. Sample A was then sent to the ALS lab for geochemical analysis, and we did 2 specific type of analysis. One was lithium borate fusion. The other one was complete digests, both measured with ICP-MS or AAS. And so sample B is still with Beak. It's in storage. So if at any point in time we need to go back to look at something, we can always go back and open up the backup sample. And with that, I just want to pass on the microphone to Roberto, who's going to tell us about data processing.
Thank you, Chrissy. Yeah, so as Christian was saying now, after we send the samples to the laboratory, the next question is how do we merge these stream sediments data with geochemical data sets from this past project, the Vistamar series, the one that you see there in blue. And the new data sets is the DeepBEAT project. So one of the difference between them, there are several, right? But one of the most important one when thinking on how to combine these data sets are that we have 4,731 catchment areas on all the data set that was sent to the lab in 2019. So we have already a time span of almost 7 years. Even though it's the same laboratory that we send the samples, maybe the analysis will change, and that's what we will take a look at now. So the DeepBEAT data set is conformed by around 504 catchment areas, but also very important to take a look at the average size of those. So on the new data set, the average is 2.31 square kilometers, while the Vistamer's data is just 0.66. So those are factors that we need to take into account or in consideration while comparing these data sets. Also that even though the 2 surveys are really close to each other, they are sitting in a similar geology, but the background geology is actually a different one, right? So those are things that we need to have in mind. Then, of course, our goal is to create a new expanded geochemical atlas, for example, like this one. This is coming from the Bistomer project. This is one of the good results of this project. This is available online, and you could see all the batch of elements that were analyzed, and we here at Beak created this as part of the consortium of this project. For example, this map is showing here the map for silver. And as for reference, we are right now here sitting on this huge silver anomaly. This is Freiberg. Welcome. And of course, now the idea is to combine our new data set with this previous one. And of course, that brings a lot of challenges, like, do we really need to do something to the data if we already send the samples to the same laboratory? And I think it will depend on your interpretation, or how colorblind are you, or which element did you take a look, right? So for example, if you take a look at potassium, this is the raw data. Here we have already mixed the data, right? The catchment areas from Bistomers and the new ones. And after applying some leveling, I don't see any different, right? So visually, sometimes it's extremely difficult. Or it will depend on the element, right? So if we see instead the zirconium, okay, yes, now I do see something is happening, we need to treat this data. And that was the question that we were trying to tackle. What do we need to do to which elements, and why? So I will show a lot of plots. So I just wanted to clarify that, for example, here on the upper row, we have the copper, and on the lower row, tungsten. And I'm not doing anything, just changing the log scale here. So for example, here is just the data with a linear scale. In blue, the DeepBEAT data, and in gray, the Bistomers data. So we cannot work with this. We don't see anything there. So we go to, instead of a linear scale, we applied a logarithmic scale. Now we see it better. But of course, the Bistomers has so many catchment areas that this is still very difficult to visually compare the histograms. That's why I will just show plots of density. So just keep in mind that even though they are kind of comparable, normalized there in a logarithmic scale, the DeepBEAT dataset have much more less catchment areas. So this is the two examples. So we are not doing anything to the data here yet. So we're just changing the zoom and the visualization of the scales to have a better comparison. So going further, okay, now I want to compare these two distributions. Are there tools for this? Yes, of course. Geostatistics have a lot of tools, and I just picked two of them. The Mann-Whitney test, it will help to compare the vertical shift between the medians of two distributions and where they overlap. And also the Kolmogorov-Smirnov test will see other parameters that are not just the median, but also the variance, the skewness, and the spread of these distributions. So these two methods will give me a threshold, and if the value is greater than, for example, 0.05, it will tell me, okay, these distributions are statistically the same or not. They are not the same. And then I will need to figure out, okay, then let's how to fix it. So after running this test for all the elements, I just found that, hurrah, we have 5 elements that are statistically identical, and we need to figure out what to do with the rest. So this means that for cobalt, mercury, potassium, niobium, and yttrium, here you have the yttrium and cobalt examples. They are from the lab with the raw data, totally comparable. If you see the histograms, and here you will see the QQ plots comparing the two distributions. So if they align with this diagonal line, that means that it's exactly the same distribution. So when they are very close to the line or parallel to the line, that means that they are very similar statistically. So then let's take a look at what happened to the other ones, right? These ones are good. And also, apart from the QQ plot and how close they are to the diagonal, it's also important to take a look to then the ones that we need to correct, how to correct them. It's also important to take a look at this plot. This is just the normalized rank. So we are ordering from lower to higher all the samples. In blue, the ones from the DeepBEAT, and in gray, the ones from the Bistomers. In this example, they are almost identical, so they are on top of each other. And we have a very good resolution. It looks like a continued data set. And this continue of or discreteness of the samples that's coming from the receptor from the laboratory. So that's something that we cannot modify, but it's important to analyze it and take a look at it because it will tell us how can we correct the data set. So in this case, we don't need to do anything. They are statistically identical based on the results of this analysis, but there are others that they are not that good. So for example, here we have aluminum and tungsten. They are very similar, but we already from the histograms, we see that they have some leveling problems that we need to solve. And some of them, for example, the bistamers will have a greater quantization of the average values. You can see it here. So it has, in general, greater values than the new DeepBEAT data. The why is this happening? There is a lot of things. We have the background geology. It could be the geology that's different. It could be the time of the experiment or the acid composition that change, or it could be that the laboratory have a new detector. There's a lot of whys. But well, we can correct this, right? So for example, when the distributions, even though it's shifted, but we have still a very good continuous discretization of the data like this, we can apply a histogram match it because we will not introduce any artifact, we will not modify the distribution shape, and we can label those. So for example, here you have again the aluminum example and the tungsten one. They are continuous enough for us to shift them with a histogram matching. That means that we will have a bin and then we will match per bin. But then we have some horrible examples. So here you will see the method that we will use depending on how good was the correlation. So you will have already an overview, okay, for all these elements, we have a problem. And this problem could be also because most of the data is below the detection limit, we don't have enough data, or because something really changed between 7 years ago and now in the analysis of this method, or simply because the laboratory doesn't have the resolution enough to see this. And usually when we analyze how discrete are the samples, we see these artifacts, right? This is coming from the receptor, from the device, from the laboratory. It doesn't have the resolution enough to have a continuous measurement, so it gives you the data in bins. So this data needs to be corrected, but we cannot apply the histogram matching, otherwise we will introduce a lot of artifacts. So the only way here is just to apply a linear correction. So for example, that will be here. So we need to label the data set, and the only way is just to apply a linear correction that will be just a constant that will shift the distributions one on top of the other without modifying the shape. That's what we want to keep intact, right? And this is another example of one of the results after the histogram matching of the aluminum. You will see the distributions here, and then you can perfectly shape it to be more comparable. So of course that will correct the data. But this is just the beginning, right? This is an ongoing project and we still have a lot to do. But well, we have now the corrected data per element that's now comparable. This is the chromium example, how was the raw data, and now how you see the level data. And also the aluminum one, you will see that right now, if you are not too colorblind, you will see some differences here visually. But of course, to create such a beautiful map as we were seeing from the Erzgebirge geochemical atlas, the catchment areas have some gaps between them, so there is no other option than to do one interpolation. In this example, this is the inverse distance weighting method to try to have a continuous raster to create such a beautiful map. So this is once again an intermediate step. This is not the final result, but this is again now the combined map for silver. And we are still here on this huge silver anomaly. So, well, keep in touch with us. One of the good results of this project should be a new geochemical atlas for the Erzgebirge, but also now including across border the Czech section. Yeah. Thank you.